Yes, doctor.
Okay, we're going to continue with this example, make a couple more comments. Oh, here. This is the program that I want you to use. This program is not mine, okay? This program was published in the appendix of this book, but one of the earliest editions. I don't know if right now, if the last edition, it's been presented again, but in any way, this is not mine. So if somebody is interested by any reason, yeah, I can share with you, because I didn't type it, my wife did. It's a very long, there are several subroutines and all of that, but it works. I made a couple of changes because it was originally to run in a large computer. So we have to adapt a couple of things to make it run in the PC. But yeah, it's available, and this is the thing I want you to use, okay? So these are the variables. I'm not going to say much about it, okay? Okay, here.
You don't share the screen.
Yeah, I forgot to share the screen. Thank you. Okay, thanks. Better?
Yes.
Okay, thank you for letting me. Okay, here you see that I have ISC and JSC, okay? And we're going to explain that, I don't know if maybe today or on Thursday. The thing is that you could have, for example, in a triangle, in an element like this, and you could have distributed force like this. Let me do a bit more realistic. Let's suppose I have something like this. Okay, so this is distributed force. And of course, you can see immediately that you have two components. Okay, so in this case, for example, let's suppose that this is my joint I, and this is the joint J. This is joint K in an element. So in this side of this element, we have this distributed force. So this is force per unit length. Okay, so in this case, this information, I will show you in a minute. This information, what is my pointer? Here. This and that are the joints, okay? In this case, it's this and that joint where you have this distributed force applied, okay? So this is something that we need to specify. And the rest is very simple to understand. There's not much to say. Here we get more information. No more. You can read. There's no problem. In this case, there was something else. What it is? It's a type of problem, okay? It's the type of problem. What is here? An opt. This is the number of options. So this is the type of problem that you have. Okay. Okay. So in our case, we work with plane stress. Okay. So in this case, plane stress means that sigma z, tau xc, and tau yz are 0. In the case of plane strain, one of the strains is equal to 0. And there are also two simplifications. Okay, so this is different. Okay, so we are working with option 2, and you see that in the data file that I gave you as an example. Okay, that's that. Another thing that may you is that there are an option in order to apply or not the weight here. Okay. Probably it's, in this case, it's the weight which is working in the z direction. So in our case, I just put it 0 because the weight is so small that it doesn't play much in our problem. Another comment. Oh, here, M out. Okay. Okay. If you want, for some reason, to see what's in the global stiffness matrix, you can set this, okay? If you put a 0, okay, you will have no output. If you put any number different than 0, then you will have the global stiffness matrix printed in the result file, okay? If it is a small example, yeah, it makes sense. But if it is a very long example, then this is an extremely large stiffness matrix. So you have a lot of numbers. It's going to be quite complex to make any sense out of those numbers. Okay, so if you develop this with a very one or two elements, yeah, it's a good idea to check what's inside this global matrix. If not, I just put it 0, so I have no matrix printed in my result file. Okay, please, if there is any questions about this, let me know. So you have to read it in detail in your group, and the more different than what we did that we have before, this is the ones that I have just mentioned. Okay, now, you need to prepare a data file in text format, TXT format, okay? So in the data file, what are you going to include? And this is what you're going to include. First, a title, okay? So it's just an alphanumeric. So it's always a good idea to include a title, okay? So you see that here, I have 80 columns. Okay, so you can, in 80 columns, okay, in 80 characters, you can type a lot of things. So I always suggest that you include a good information about the title. So when you have the response, the results, you can see what type of example you're analyzing and what size of mesh is using or something like that, okay? So it's always a good idea to include a good title, including a lot of information. You have 80 columns to include that. Basic parameters, let's see, Mr. Sanchez, what do you think is NNP here in the second? What do you think? What did you imagine? What is NNP? Mr. Sanchez, are you there?
Yes, doctor. I'm thinking. Let me a minute. NNP.
Number of what? Number of what do you think?
Nodes.
Exactly. Points.
Okay, point.
For some reason, instead of joints, he uses points. So this is the number of joints. Makes sense. That is extremely important for any partition. And NL, Mr. Sanchez, what do you think? NL.
Elements, number of elements.
Exactly. And mat.
Matrices?
No. Number of materials. Materials. See, so for example, you could have a beam, okay, a beam composed of 2 materials. So you could have this partition like this. But down here, okay, in these elements, you have one Young modulus, one Poisson ratio, and a different one for the upper ones. So in that case, you could have more than one material. This is the number of distributed forces, as I explained before, okay? Options, and this is the number of FEM. Anyway, we'll see that in a minute. This is print out options. You have two values here, in and M out. If you put here a 1 or something different than 0, these are two numbers. In that case, you will see that you will have the stiffness matrix of every element printed in the result file. If you have a 1 or a different than 0 value here for the second variable, in that case, you will have the complete global stiffness matrix printed in the result file. So expect a lot of information, a lot of numbers. Now, here, you decided how many materials you are going to include. So according to that, you're going to have one of these lines for every material. And in every material, you're going to have Young modulus, Poisson ratio, density, and the thickness for every material. So if you have the same material with two thicknesses, in that case, you have to include two materials. And you have to specify different thicknesses here. In your case, Isaac, you would include at least two, right? Because you have a reduction in thickness in the central part of your specimen.
Yeah.
Okay, let's go on. Then, remember that every element, okay, every joint is defined according to the position. So you see that here is the position, okay. These are the values of the deflections if these are specified. This is a code that sets up the certain restrictions according to restriction. And this is the number of the joint. So this is one line for every joint. So here you have the number of joints. So you need information from line 5 in the same number of the number of joints. So you need one line 5 for every joint. Similarly, for line 6, you specify the number of elements. So you need line 6 in NL repetitions, one for every element. Here, you have 4 joints. Okay, so in general, this program was set up to work with this type of elements. Okay? But the problem is that in our case, we are working with triangles. So for this triangle here, okay, since you need 4 joints, what you need to do is I, J, K. And what you do is, would you repeat the number of the last joint, and the program understands that if K and L are the same, you are using triangular elements, okay? M type, that depends on the material. If you have 2 or 3 materials, you have to specify for every element what type of material you are using, okay? And finally, you have the surface tractions, okay? Remember that up here, you specified that you're going to include this many tractions. So for each one of these, you need line 7. So you have 1 and 2 joints, the 2 joints that define the side where you're going to apply the tractions. And then you have the surface traction at the beginning, at the end. And in the X direction, this is the X direction, this is the X direction. And something similar for the Y direction and Y direction. So let me go back. here, for example, see, this little value here will have two components in X and Y, and this large value here will have a component in X and Y. So this is the beginning in the X direction. This is the end in the X direction, beginning and end in the Y direction. So that's why here you need 4 values, okay? Surface traction in X, surface traction in X, and in the beginning at the end. So what they do is they approximate the distribution with a linear distribution. Questions, people? Questions so far? Good. These are notes. Let me, here I have these 2 values, n-opt and n-body. Let's see what they mean, n-opt here. In this case, n-up, we choose 2 because we're using plane stress, right? Okay, so here this is 2. And n-body, it's here. We choose 0 because we are not going to include weight, okay? This is for this and that. So you see that the data file is simple. There are some special notes here. This is interesting, okay? Here. Remember, this is, you put it in here. So you specify the type of restriction or the type of load that you're going to apply, okay? Okay, here. So if you select, let me find my pointer. Where is my pointer? Here is my pointer. So if I select 0, so that means that you have to specify the load in the X and Y direction. Remember that specify a value of 0 is something which is, 0 is a known value, okay? Similarly, if you choose code 1, that means that you know the load, the displacement in the X direction, and you know the load in the Y direction, okay? Code 2, the opposite. You know the load in the X, and you know the displacement in Y. And code 3, you know the displacement in both directions. So in our case, for example, if we have this, something like this, what would be the code here? Somebody, anybody? What would be the code for the joint that I'm showing? Mr. Ramon, can you answer my question? Mr. Ramon?
I'm here, doctor.
What would be the code value for this joint?
What joints?
This joint.
Is 0?
No, the code. You see, this variable can take values 0, 1, 2, and 3. What do you know about this joint? What do you know about this joint? What do you know about this joint? No? Okay, let me go to somebody else. Mr. Leon, what do you know about this joint that I'm showing you here?
We know the displacement.
Exactly. So what would be the code value for this joint?
3.
Exactly. And for this one here, what would be the code value? Miss Vega, what would be the code value for this joint, Miss Vega? What do you know about this joint? Miss Vega?
Code number 2.
You know 2? So you're saying me that you know the load in the x direction and you know the displacement in the y direction. You know how much this is going to bend downwards? I don't know. I don't know that. Mr. Iñiguez, what will be the code value for this joint?
Good morning. The load in y direction.
What would be the load in the x direction? What's the load in the x direction? The external load in the x direction, Mr. Iñiguez? It's going to be how much? How much is the load? How much force do I have in this direction?
It's 0.
Exactly. So you know that value. So what's the value for the code variable for this joint? Since you know values of the forces in the x and y direction, what's going to be the code value, the value of the code variable? Mr. Peralta, can you help us?
Yes, doctor. Good morning. Is the 0 code?
Exactly. It's 0 because you know values of the force in the x, the load in the x and in the y direction. So you know this and you know that. So the code is 0. So according to the type of restriction or load that you have in every joint, you can specify the type of load at the joint that you are defining. Okay? Here, this is an example. This is very similar to what we did, except that the forces are in the x direction. Okay, so this is a plate simply supported on the left, and then you have these two concentrated forces to the right. And this is the data file. So I have 4 joints, 2 elements. This is the one material. This is plane stress, and I have no weight. I have not printed. So neither the element stiffness or the global stiffness, nothing is printed. This is the Young modulus, Poisson ratio, density, and I don't know what else is. So these are the joints. Yeah, okay, this is 3 and 3 because we know the displacements. Okay, let me go back. See, this is code 3. And the other 2 are code 0, as we said before. So these are the position, XY, 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 XY. So these are the positions. And these 2 are the related values. In here, we said that we know the displacement, and the displacement are 0 in X and Y, 0 in X and Y. These are the forces. This is force in the X direction, this is force in the Y direction. Since we have only one force in the X direction, that's all what we have. And this is the connectivity part. This is the connectivity. So we have 2 elements. These are the joints. And you see that the 2 are the same because these are triangles. And the last one I remember, oh, this is the material. So this is material, so this is mat. So material 1 means that these are the properties of that. Oh, the last one is the thickness. Questions about this, people? Questions?
Please repeat the line 9 and 10.
9 and 10. So these are the elements. Okay, let me go back here. Element 1 is this, and that. Okay, since the program was developed to include elements with 4 joints, what we do is we repeat this element, this joint, I'm sorry, and put again joint 2. When you put this 1, 3, 2, and 2, he considers, he knows, the program knows that since these 2 are the same, in that case, this is a triangle. That's why we repeat here, 1, 3, 2, and 2. Okay? And the last one, this one, means that the material properties for this element is the material name number 1. So in this case, we have only one material, we have only one line. So for this element and for that element, so he's going to consider this is material number 1. So in this case, joint modulus is going to be 30 e to the 6, etc. And the thickness is going to be 1. Here, this is the thickness. Okay? That's what it means. Okay? Mr. Wagon?
Yes, doctor, thanks.
Okay, no problem. Okay, after that, this is the results. These are the results. Okay? You see that you can identify, here it says output. So up to here, okay, this is data. And these are results. Okay, so here you see the displacement in the X direction and in the Y direction for each one of the joints. You see that this value, e to the -3, e to the -3 are very small. Okay. And also, well, the displacement in the Y direction is even smaller. So you see that this value is not the same as this one, even though we're expecting that if we apply the same force up and down, the displacement should be like this. Okay, this should be like this. So the displacement in U should be the same. It is not. It's close, but it's not. Why not? Because the partition is not symmetric with respect to the central there. And you see that in the vertical direction is very interesting, but the vertical motion of the vertical displacement of joint 3 is 0. Okay? And in the Y direction, this goes up. You see that this point, where's my pointer? Here. So this point should move downwards, but it doesn't move downward. It just comes from here to here. And this one here comes to the right and up, which makes sense. So what it's telling us is that we should do a better job in trying to partition this domain. Down here, we have the sigmas, and of course, every sigma will be positive on the here. So we have sigma x positive, I'm sorry, everything is positive, makes sense. Sigma y, so this is to the 3, this is to the 2nd, so this is much smaller than this one, makes sense. Tau is very small since there is no shear load. So everything is just pulling up. Okay, when we return, we're going to talk about your project that you have to be completed in groups, okay? So let's take a 5-minute break and then we will return. Please, Engineer Isaac, get ready with the groups the members of the group so we can check if everybody is correct. Okay?
Okay, there are 5 groups so far.
Okay, people. Right now, we need you to make up your mind because the time is running. Okay? So try to organize groups because I want you to start working. Okay.